So hopefully by now you can see a need or the reason to program on the GPU. If so, your next question might be to ask yourself, well, when would I actually develop programs for the GPU? Well, converting a program to take advantage of the GPU is by far not a simple task or a cheap task. Therefore, there's a need to determine which code would be most efficient on the CPU and which would be more efficient on the GPUs. There's been a lot of research conducted to justify this very thing, to determine which processes would be best run on the GPU. Some of the processes are listed here, which would be most applicable for the GPU. Some of these are, of course, graphical rendering. That's always been main kudo for GPUs. You also have data parallel computations, some computationally intensive tasks, which would be ideal for GPUs, are some scientific and engineering computing problems, physics simulations, matrix algebra, image and volume processing, global illumination. As you can see, there are a lot of different processes and different uses for the GPU. You can see significant amount of scenarios which it would be advantageous to take advantage of the GPU's processing capabilities. So now that we've discussed all this, before we get into anything else, I would like to take a quick sidestep to talk about parallelism. In this slide right here, we talk about data parallelism. Well, there's actually two types of parallelism. There's task parallelism and data parallelism. Well, you might be asking yourself, why do I care about this? Well, data parallelism usually runs best on GPUs, whereas the task parallelism is well suited to run on the CPUs. In order to know when to program on the GPUs, it's a good idea to know the difference between these two types of parallel programming. So, task parallelism is defined as where each processor executes a different thread or process on the same or different data. These threads can be the same or different codes, and that's the main thing, they can be different codes. So let's take for example an Outlook. So Outlook has an address box, an inbox, a calendar. All of these different parts of Outlook run on separate threads. They each contain completely different separate code and have basically nothing to do with each other. So for visualization, let's say you had a GPU, he's doing a unicycle, he's juggling, and he is balancing flowers on his head, and he does all these three tasks, which are very different, very well. Now let's say someone asked him to juggle 80 or 100 balls instead of just 3. Then he would get bogged down. It might almost be impossible for him to take care of this. That's when you go over to the GPU. GPU is really good at data parallelism. Data parallelism is defined as when you distribute the data across different parallel computing nodes. This is where you perform the same task on different pieces of distributed data. So you're performing the same exact task. So you have this same exact task of juggling, but it's a lot of juggling. You have 80 balls instead of just 3 balls. So the CPU might just want to hand that over to the CPU might just want to hand that task over to the GPU, so that the GPU can distribute this task among all of its little ALUs, algebraic logic units. The GPU would get this done a lot quicker and a lot more efficiently, with a lot less stress than the CPU would.